Gracias.
Okay, so it's a pleasure to introduce to you Margarita Hernanz. She's a research professor of physics at ICE. She received a PhD degree in physics from the University of Barcelona in 1996. She was teaching at the Barcelona Tech University from 1984 to 1990. After that, in 1990, she joined to CSIC as a tenure scientist, first at CEAP, and since 96 at ICE, when ICE was founded. She is a research professor since 2008. Her research focus in the last stage of evolution, such as nova, white dwarfs, and Taiwanese supernovae, but she's focused on high energy emission, X-ray and gamma ray. In the last 20 years, she has been largely involved in the development of instruments for X-ray and gamma ray missions, being PI of multiple projects and instruments such as WFM of the China EU X-ray mission, GRI, Dual, Astrogram, GRAST, among others. She has more than 150 papers in SIA journals, and she has several PhD thesis advice. So please start. Today she will talk about NOVA. So I will tell you when the time is ready for questions. Okay.
Thank you.
Welcome.
Thank you a lot for the presentation. Okay, so the topic is explosions of white dwarf novae. Some of you have already heard about that from me before, but specifying two specific aspects, which are the lithium production, lithium-7, and the acceleration of particles, so the origin of cosmic rays. Avanza, pasa. Okay, just as you probably already know, nova doesn't mean that it's a new stellar, which is the origin of the name, but it is a new star, apparent new star that appears in the sky because it becomes brighter. So this is the origin of the name. This is a picture of Nova Cygni 1975, a very famous nova, very bright. Of course, there have been many more. And then, as we will detail a bit later, nova is an explosion of a white dwarf, but an explosion that takes place on top of the white dwarf, an explosion, thermonuclear explosion of hydrogen. And to have that, the white dwarf should be in a closed binary system, should have a companion. Okay, so let me see the title. So white dwarfs white dwarf stars are the endpoints of stellar evolution of stars with masses less than 10 solar masses. And since they don't have more available nuclear energy, then they become degenerate. They are sustained by the degenerate gas of electrons, and then they just dim and don't have explosions if they are isolated. The chemical composition is helium, carbon, oxygen, helium, carbon, oxygen, the more frequent ones. So they have typical masses around 1 solar mass white dwarf. And the maximum mass they can reach is the Chandrasekhar mass, where they become unstable and explode as supernovae. As I said, once isolated, they just cool down. They are very interesting. There is a lot of work being done here by Jordi and myself several years ago as well about the cooling of white dwarfs and its implications for many topics. But what we are interested now is what happens when they are in a binary system where there is an interaction, in the sense that mass, hydrogen-rich mass comes from the companion, and then they are, so to speak, rejuvenated, and then can explode either as novae or as thermonuclear supernovae, type I supernovae, which are not the core collapse supernovae that come from massive stars. Okay, so this is a scheme of the way that will be here. So this will be the companion. In this case, it will be a cataclysmic, the so-called cataclysmic virus, where this is a main sequence star like the sun. And then there is mass transfer, and there are rotation disk forms. But we have another possibility, which is that one, which is when we have a companion, which is a giant, and then there is the possibility also, and this has been observed, the formation of a disk like here, but which this is what, okay, but also there is the wind of the giant. So then we can have nova explosions in both types of binary systems. These are called classical novae, and these are called symbiotic stars, because these symbiotic stars are observed even, of course, before they explode. Well, this phenomenon is recurrent because the star is not completely disrupted. Let's see this in here. So the effect of the accretion of the white dwarf depends on the mass, luminosity of the white dwarf. And then on top of the white dwarf, there can be this degenerate burning, which is related to the fact that the doesn't behave like an ideal gas, the matter there. And then there is not a self-control, say, to expand and have a burning, normal hydrostatic burning, say, how we have in the sun or in many stars. So then there is goes out of control. There is what is called a thermonuclear runaway, and this means that there is this ejection of matter. So one fraction of the mass of the star with speeds around thousands of kilometers per second. And the white dwarf is not disrupted. So after the mass is ejected, because it expands at high velocity, so it can escape the gravitational field of the white dwarf. Then after several thousands of years or tens thousands of years, this can happen again. So it's a recurrent phenomenon. So this is the case of classical novae. And then we don't know, well, it depends on the conditions, how often they recur. But in the case of having this companion that is a giant, the accretion rate is, so the rate at which mass is transferred from the companion is higher, and then the conditions to reach the status where there will be the explosion are reached before, and then they can have explosions more often. And when this recurrence period is less than 100 years, so to speak, then there has been the possibility to observe more than one from ourselves as observers. So there are 10 known in our galaxy. There are more known in other galaxies, in Andromeda and the Magellan Clouds. But in our galaxies, there are so it's called 10 historical recurrent novae that have been recorded more than once. Some of them 4 times, 5, some of them only 2 times. Well, another possibility of the for a white dwarf is that instead of burning hydrogen, or perhaps after having burned this hydrogen, this is not clear, they just have reached the Chandrasekhar mass, and then they are unstable, and then there is a central carbon burning that propagates outside, outwards, and then this means that there is a total disruption of the star. And this is the supernova. It is a supernova of the thermonuclear type, so not the core collapse supernova. And the kinetic energies that here were 10 to the 45, here 10 to 51. The ejected mass that here was, say, 1 divided by the 10,000 solar masses, with the solar mass being the mass of the star, in typical mass of the white dwarf. In this case, the ejected mass is the global, all the mass of the white dwarf. And the ejecta velocities here were thousands at most kilometers per second, and here they are around 10,000 of kilometers per second. And well, the probability here, or the rate, is 1 per century, in principle, in the galaxy of Type Ia. So this just was to make a very fast comparison of novae and supernova. But well, one can understand that it's not impossible, even that this is not completely clear by now, that a nova that has, after having experienced several hours, can also explode finally as a supernova. Since it's a recurrent, it grows. It depends of if it increases or diminishes its mass after each eruption, and this is not completely clear. In principle, it's thought that they lose more mass than what they eject, because there are some enrichments in chemical elements observed that come from the dredge up of matter from the white dwarf, but it can also happen that they increase in mass. So if they increase in mass, they can reach a Chandrasekhar mass, and a nova can finally become a supernova, or if not, so this is a discussion not yet settled. What is the origin of type 1a supernova. Single degenerate scenario will be this one we are saying, a companion that is not another quite dwarf. But there is this problem if you really reach the Chandrasekhar mass or not, because you can lose more mass and you are doing nova explosions, and the double degenerated when you have the merging of two white dwarfs by gravitational radiation if they are close enough, and then you can reach the Chandrasekhar mass by this merging instead of reaching it through accretion. Okay, so this was the pre-introduction, and this will be the topics I pretend to comment just without entering all the details, but just some discoveries in the, say, 10, a bit more than 10, in fact, last years about novae that have been especially relevant. One is the confirmation through observations. So the confirmation, because before it was only theory, now it has been observed, of the lithium-7 synthesis that comes from the beryllium-7 decay during the explosions of novae. And this is very important for the origin of lithium in the universe. This is a topic that has been studied from several years. And then, well, it's not completely clear. And knowing if novae contribute or not changes a bit the scenarios. And now it looks like this can be the case. And another part is the high energies. There are also X-rays, very important for novae, but we are not talking today about X-rays. Regarding gamma rays, we can divide, but this is more, we can divide gamma rays, say, in high energy gamma rays and very high energy gamma rays. Of course, very high energy gamma rays are a subset of high energy, but from the point of view of observations and the instruments that are needed to detect them, it's important to make this distinction. So both of these gamma rays are emitted, this is general, not only related to nova, if you are able to accelerate particles. So in case that novae are able to accelerate electrons, we can produce these gamma rays, but not these gamma rays. In case of that novae are able to accelerate electrons and protons, we can produce this, and also this, of course. But the electrons produce one. So more or less to simplify. And then in this sense here, there was a researcher from France, Vincent Pichel, that made a sabbatical stage here in 2006, and then 6-7. And then there was the explosion of one of these novae that are recurrent. So this one exploded there, then in 2006, when he was here, in fact, and it has exploded in 2021 again. It has this nova, which is in one of these that have a giant companion. It has a period of 15 years and quite exact. There were previous observations also before 2006. And then we made, thanks to his knowledge in charge, acceleration of particles, well, just looking at the observations, there were many observations when there was this explosion in 2006, but there was no instrument to detect these gamma rays. The prediction that provided there is an instrument that can detect this nova could have been detected. And this is very interesting because now there was a new explosion and there was already the Fermi satellite, and then it detected it. And also it has detected other novae. So this was, we made the prediction before this could be observed. Afterwards it was observed since night. And also, and last but not least, very high energy gamma rays, which really requires the protons also being accelerated. And we predicted that they were accelerated also. And many people didn't say, well, are you sure they were? Based on the observations in X-rays and had different observations of this explosion in 2006, but no gamma ray observations. And then, well, it was detected by, well, now in 2021 with HESS, MAGIC, even a prototype of the Cherenkov telescope array. So 3 detections of these very high energy gamma rays, so energies larger. So this is what I wanted to comment, but probably I don't have time to enter in many details, but we will see a bit of these 2 topics, say, or 3, depending on we divide this in 2 or not. And well, of course, this has consequences for the origin of the cosmic rays. In general, supernovae, of course, will be will originate will be originating most of the cosmic rays that we have in the universe. But novae, this is true, and now it has been demonstrated, not only predicted, also will contribute. So this is well, so for lithium, I will go fast without entering the details, but most of you know that the so-called light elements, lithium, beryllium, and boron, cannot be produced and preserved. So they are produced, but they are destroyed inside the stars. These are the abundances, solar system abundances. They have very low abundances. So their origin of lithium, beryllium, and boron, different isotopes of them, in particular lithium-7, are much smaller than the abundances of other elements. So, well, there are three main sources that are known since long. During the Big Bang, for sure, there is production of lithium, beryllium, and boron. Also, spiration reactions, which are reactions between that happen in the interstellar medium during these cosmic rays, accelerated charges and atoms that are there. And stellar origin. Stellar origin, in principle, is difficult because they are fragile. Well, there are other aspects of nuclear physics that make difficult to produce them. But anyway, there are reactions where they are produced. We will see in a moment. Also, for instance, in the sun, they are produced, but they are destroyed. So since they are fragile, even if there is a supernova explosion afterwards, or well, anyway, it's not, you cannot produce them in such a way that afterwards they can be expelled, unless you have what we will comment in a moment, the so-called Cameron-Fowler mechanism that transports them by convection to zones where they are not destroyed, and then they are expelled there. So you should transport them somewhere where they are not destroyed. And then this means that it's easier, say, or more feasible, only feasible, in fact, to produce them, to have them produced in some way in stars if they are produced in the external shells. Red giants means the external burning shells, hydrogen, helium, hydrogen burning shells, and in nova, that, as I mentioned, are burning hydrogen. Why hydrogen? Because, as we will see, well, I will see in a moment, they are produced through the same, so the same chains, nuclear chains that produce helium in the sun, in many stars. So if you have this in the surface, and we have convection, we can preserve them, and the beryllium and the decays to lithium. Well, so this is a topic that also is a standing topic, but what was very interesting is that, again, we need the observations to demonstrate things that for the first time in 2015, it was detected. And then I was very honored that they called me from Nature to write a news and views, because we, with Jordi José, I was my first PhD student, and now he's professor in the Technical University of Catalonia. In his thesis, he made updated calculations, and this was one of the papers we did also with Jordi, mentioning that lithium-7 could be produced in novae, what had never been observed, and well, in this case, it was observed. So these were the first predictions, but ours were more based on better models, say. So already Arnold and Norgard in the 75 mentioned this. Statfield, that we are in touch with him, he's even older than myself, but he still continues to do work. Already in the 70s, they made what is called a kind of post-processing. So it was not combined the nuclear physics study, the nucleosynthesis, with the hydro model, and we did for the first time this combination of a whole model, say, of 1D, like the model was 1D, a hydrodynamic model to simulate the explosion of white dwarfs as novae, and related to a detailed treatment of the nucleosynthesis, because you should be very careful with that. And then we obtained some predictions. Then this is very long to explain, but if you have studied a bit of stellar physics, you know that from the proton-proton reactions, one produces, transforms 4 atoms of hydrogen in helium, okay? And you release 2 electron neutrinos. But also in the path, you produce here beryllium-7, okay? So you have formed first the helium-3 from protons, only protons, we have. And then here you produce beryllium-7, And well, so this part from here is what is represented. This is the figure I suggested that I made for this nature view, muon views. It was more visual. You have this one. This is the same, no? Helium-3 plus helium-3 releasing two protons gives helium-4, but also if it captures a nucleus of helium-4 produces helium-7 that can be destroyed, say, through a capture of a proton to give boron-8, but can also decay to lithium-7. So this is a radioactive decay, an electron capture. This has some lifetime, half-time, this one, and also releases gamma rays because the daughter nucleus is always excited state and it releases this, the nucleus releases photons of half mega electron volt. So this is the process. The thing is that you should combine this, so nature should combine that in the form of not having this in the interior. We have this in the sun, but we will never eject this beryllium that produces afterwards lithium. But if this happens in the external zones and you can transport the beryllium before it decays to lithium to a cooler zone, then finally you can produce the lithium. So this is possible in novae and also in external cells of GV stars. In fact, Jordino and Carlos Javier had made observations of lithium, detections of lithium in some giant stars. But as I said, until this paper of 2015, there was no detection in novae. Well, so this is the prediction we made. We will see just that this was the maximum we could obtain as a mass fraction. So it's just 1 divided by 10 to the minus 6 or 10 to minus 5 of lithium with respect to the other elements. So it's not much, but it could be observed at some moment. Well, and this is when it was detected. So this was the production. And then, but just these people here know much better than me, you probably, and Luis or others know that I consider this for me really was spectacular, but I imagine that this is done every day nowadays to really distinguish the beryllium-7 because it's this is an isotope. There is beryllium-9 as well, but we are interested in beryllium-7, not beryllium-9. The beryllium that produces lithium is 7, so they could distinguish. Well, this is high resolution, the absorption lines here with the Subaru telescope, an instrument here. So they were able really to distinguish this. So the different lines distinguish. And also, of course, it was important to see the blue shift because it was blue shifted. So there is expansion there at velocities that corresponded also to the blue shift of other normal lines that are detected in hydrogen calcium. Well, there has been controversy, even that this was published in Nature and continues, but now it's more or less solved about how they determine the abundances, because one thing is detecting the line, which is already important, another thing is how you transform that. But anyway, in this case, in this paper of Tajitsu, Subaru, they predicted this number that in fact is larger, 5 to 10 to the minus 5 is larger than what I showed before, the largest value we obtained. So, well, this is just to show, probably I have forgotten some of them. Well, there were other papers afterwards from the same team there. And these are from a team where we now participate now with Luca Izzo and Paolo Volaro that are observing now with ISO the US instrument on PLT. And they have detected in several novae, observed a lot and have detected. So now it's not that all novae have beryllium, but in several of them, yes. Well, then we move to another related topic, which is the high energy, so gamma, in this case. Forget about X, as I say, so lines that can reveal as well, lines in the gamma ray spectra that can reveal this decay. So this, of course, would be crucial, this detection, because if you detect this line, you can measure directly the amount of beryllium. But well, this has not been detected yet, so this is still open because here we enter in the problems of the instrumentation And in the gamma ray regime, it's very difficult to progress. Well, it's not because it's not well done, because there's something intrinsic, but we are not discussing this now. So, well, just to say that, of course, this is related to the topic of gamma rays from novae, supernovae. That's also one topic where we have been working here in the Institute since long, and also trying to have better instruments in the future. Well, so let's just comment that, as I mentioned in the beginning, we have the very high energy gamma rays, but now we have, I'm talking about now, of this radioactivity, so nuclei that are radioactive, as we have in the lab. And this has nothing to do with the acceleration of particles, it's just the nature of these nuclei. So radioactivity in the ejecta of novae or supernovae, of course, traces directly the nucleosynthesis. We are just looking, measuring, if we detect them, the radioactive nuclei that are produced there. And then these transitions are in the range of the megaelectron volts, not in the range of hundreds of megaelectron volts or gigaelectron volts, as the gamma rays produced by other effects, inverse quantum, pion decay, that are observed with other instruments. So just to now mention this, then, which have been the instruments that could have been detected and have, in fact, tried to detect. So it's not that they don't know. We did a Comptel telescope on board the Quantum Gamma Ray Observatory. It was in the 1990 decade. No, even that there was this nova that I showed at the beginning, 75, very bright, but they pointed to it. But, well, this one or another one, because it was, anyway, they pointed to some novae and bright novae, but they didn't detect neither beryllium, neither other radioactive nuclei. An integral speed that is still active now, but that has not have success. So, well, this is just to show you, this is what I showed when I was teaching in the master, the list of, there are not many, the list of interesting astrophysics radioactive nuclei. So there are hundreds of thousands of radioactive nuclei, but the ones that really we could observe in supernovae or novae are these ones, with their characteristic here, lifetimes and energies. And here in the case of nova, we have these two. We are talking about lithium now. Okay. And just to mention, well, that it's aligned with this energy, as I mentioned in the scheme before. And just to mention, well, this is a bit technical, but just that the electron capture is the one that we are interested in, because the decay of beryllium-7 can also go through a E plus or a beta plus decay, which is equivalent with respect to the final result, but not equivalent nuclearly. So it's different to have an electron capture, which means the electron that enters in the nucleus, or having an emission of a positron. Even that has, again, the residual step. So we, this line is very interesting. As I said, what would just happen, say, the emission of this line in 10% of the decays, global decays of beryllium to lithium. And this, of course, this should be taken into account. This goes against, say. Well, these are models that we have been making with so long ago. After having this nucleosynthesis, we also made computations of the lines. We are, by the way, updating them now, but well, there are not many changes. So there is this line. Here, this is the spectrum, a gamma ray spectrum. This is 0.1 mega electron volt, 1 mega electron volt. Here we have this 478. And this is not very interesting, just the light curve. But it means that, of course, we should observe the nova very soon, and not, we cannot observe it 1 month or 1 month still, but not 2 months after the explosion, because the flux will have decay a lot. Well, so the instruments, as I mentioned, are these ones. And here I have not, well, then there's the web page, and there is some delay as usual. They say 2025, and now they say, or 23, they say 2027 as the expected launch, but finally they will be an emission, because integral will end after 25 years, which is not, well, 25, no, sorry. No, this is, well, anyway, 20, I think I made a mistake here, 2002, not 2012, when it was launched, sorry. So it's we have celebrated the 20 years of integral in 2022. So now they will turn it off, which means that there is a control re-entry. So it will still be during 2 or 3 years, I don't remember now exactly, active, but just changing the orbit to enter in a way that there is a minimum debris. They should do that. They do that all the percentage. So it could perhaps do observations, but not as we want. No? So it will, I mean, the integral users group, and now they are trying, the PIs of the instrument, the groups, to have some money to just do some science during this pre-re-entry. But anyway, it won't be active. It will be in the post-operation phase in 2025. So this is the last year operation. So we wait. In fact, there is a possible nova this year, one of these recurrent like RS Oph that is much closer. So eventually it could be observed. And then there will be a COSI from NASA that has been approved. It's better than integral in some way, yes, but it won't be very easy to detect novae, except that it will have a wide field of view as compared to speed, the instrument here, the spectrometer, which means that it can catch eventually supernovae as well, of course, several in the field of view. And this is good because then you can accumulate observing time without having to dedicate all the time to a point source. Well, let's now move, and this is the final part of the high energy gamma rays. Okay, so the ones related to the acceleration of particles. So the high energy gamma rays from novae have been detected once launched. Fermi, was launched in 2008. Fermi is a satellite for gamma rays from NASA. It's active and very successful. And it has a large area telescope that has a very large field of view that does continuous surveys, has detected a lot of neutron stars. Well, it's very productive and interesting, provides interesting results. And in the case of novae, it detected them. So this is what I'm going to show. This is what we predicted, as I mentioned before. High energy acceleration of particles, protons, electrons. So this was demonstrated, but of course it couldn't be demonstrated until now, in this recent eruption in 2021 for this nova, but it detected several other novae. And the very high energy gamma rays, only in this case, so MAGIC was active, but in fact it didn't point well, or we don't know what happened, because it could have detected RS Oph in 2006 already. But well, there are other new ones, but anyway, now it has detected also this RS Oph well. So one of these novae that are recurrent, okay, that explodes. So, well, then what happens? Just in a few words, what's the origin of this acceleration of particles? Then we can have two types of shocks in novae, referring to when there is the explosion. On one side, first of all, there are the shocks between the mass that is ejected, and if there is a companion that is a red giant, if not, this doesn't exist, there will be then also so there will be these external shocks that will be important, okay? But in the case where there is not a red giant companion, these external shocks don't exist. There is some circumstellar matter, but this is not so relevant. So in the case of these recurrent novae, the ones that have the giant, we expect that these external shocks will play a role. And this is the case of RS Oph, and this is the one that was detected, say more, is the brighter nova detected in gamma rays, in these high energy gamma rays up to now. But there are also, and this was not very well known, and thanks to the observations of Fermi, now it's better known, there is the expectation that there are also some kind of internal shocks during the mass ejection, okay? Not so, because that's matter like the giant companion, because there is nothing, the main single star like the sun is there, but this, so in principle, it was thought that these internal shocks were not as important, but they can exist. And now we know that they play an important role. So related to these shocks, then there can be acceleration of particles. And then when you accelerate leptons or electrons, you have we show this in a figure now, inverse Compton, which means these electrons become relativistic, and then they have the inverse. There is an inverse Compton effect, which means that the normal photons that are there, the photons from the radiation of the nova, of the giant, but in principle there are more from the nova when it explodes, no? Then 10 to the 5 solar luminosities or something like that. Then these photons will increase their energy because they interact with the relativistic electrons. So this is a inverse Compton effect. Okay, the Compton effect is just the contrary. You have an electron that interacts with a photon and then it decreases its energy. But if the electron is relativistic, then the photons increase their energy. So it's a way to have gamma rays. So you transform, so to speak, the normal radiation of the nova in the gamma rays. So the photons that are not gamma rays, but are visual or ultraviolet. Okay. So this is one thing. And the other is hadronic, which means that if you have protons, you accelerate protons, so it's in which we predicted and has been demonstrated that is the case, then you have pions, and these pions produce pions of different types, but in particular neutral pions, and then they produce also gamma rays. Yes, photons with quite large energies. Larger in the case of the pion decays than here. But here you have broad range, and here it's more exclusive, say, in the sense that you really produce gamma rays of higher energy. So you hit high energies. But anyway, so it's that. So photons with energies larger than 1 MeV, and in this case, larger than some GeVs, G electron volts. Then what has happened in these, say, 10, 15 years since the launch of 40 years almost of Fermi, is that several novae, normal, say novae, of course, normal, they are bright, the ones that are detected, but anyway, several novae have been detected, but not only the ones where there is a giant companion. This is just one in all this time, which has been this RS Oph in 2021, in second eruption after the 2006 one, but also in normal classical novae. So then one sees, okay, then these internal shocks that we were mentioning should play a role. Okay, this is a bit the new thing that gamma rays have helped to have contributed, say, to the understanding of novae that we and others had predicted before. But the prediction of acceleration, it's only we, Statichev at the epoch. Now everybody agrees with that, but at the epoch it was not. Look at that, this perhaps would be impossible. So this is a press release from MAGIC, from the right to the detection. Also they asked me, and I made a newsletter for the CTAO newsletter, a comment about that. But it's nice, I like this. This graph, no? Because you have the red giant. So in the case of the companion that is a white dwarf, sorry, a red giant, it's here. So there is this shock will be this ejecta with the white dwarf matter is very, and here we have the wing and the white dwarf. Then here what you have is electrons and protons accelerate, and this is just a representation that once produce pion decay, it's hadronic emission and hadronic origin, and the others. So it's what I said. So let's explain. Well, I understand it's a lot of information in not much time, but it's just to understand that in this case, one can make models, and you have this expectation that you have both electrons and protons that are accelerate, and this produces gamma rays. Well, which instruments can detect that? Well, Fermi, as I was already advanced in 2008. It's a satellite, so it detects up to some energy, but not if the photons have energy larger than the threshold, what some tens of electron volts, they cross the satellite and they are not detected. Then you should go to the Cherenkov telescopes that are on ground, and what they detect is the Cherenkov light produced by the interaction of these very high energy photons with a larger, the ones that cross the satellite, say, the gamma ray satellite, with the atmosphere that produce Cherenkov light that is detected from ground. And this we have here, the colleagues identified that have worked a lot on MAGIC, and there are other instruments. This is in the Canary Islands, the Roque los Muchachos. Okay, so we have these two possibilities. But the MAGIC detects only the very high energy photons, and Fermi detects the ones that reach up to some giga-electron volts, but not the ones that have higher energies. Well, then the first detection, this was by Fermi. So just 2 years after being launched, in fact, the detection was a bit before, 2010, so 1 year and a half, say, after it launched, it already detected one nova. In fact, it's one strange nova because it's like this RS Oph, so it has the giant companion is a nova that was not recorded as a normal nova, but it has been then observed again. Well, it was known that this system existed, so it's one of these types. So this was the first detection. This is just to show, well, it's very simple, that these spectra are not as rich as other spectra of X-ray, just this, you see error bars. Well, okay, so 100 MeV, this is 10 giga-electron volts, and we cannot go further to higher energies. So the important news were that afterwards, so it started to detect, and I have not checked now how many, but at least a dozen or even more, perhaps, have been detected by Fermi. But then are not so many with the giant companion. So the first one, yes, by chance, said, okay, this fits. But there was still the problem that what happens with classical novae, and we detected them several. So this was the first detection, so in science, of a classical nova, so a nova that has a companion that is not a giant. So this should be related to these internal shocks, the acceleration of particles that produce the gamma rays detected by Fermi. Well, this is just the details. So, and this is a bit complicated, and this just to mention that there has been, well, Metzger, we were in a conference there, this was New York, it has not changed, on Columbia University, made models of the acceleration, detected models. So, well, but the problem is how you generate this shock, what is the scenario? And then related to Laura Chumil, the paper in Nature, so this has been very important. The predictions and observations, sorry. What they saw, and this was thanks to, in fact, it started with this paper, that this was related to observations in radio, that they saw some, in this nova, a nova that had been detected by Fermi. So the thing is that they suspected, and this is, well, makes sense, that there is no symmetry here in this process, in the sense that, and this is what was seen in radio, because in radio you have, and much better spatial resolution. So they saw some dots. This is not shown here. This is in this paper. This is the interpretation afterwards. They saw some dots somewhere, and then here, apparently there were some shocks concentrated in some place. And then the interpretation was that the nova first ejects some equatorial, some matter from the equator that is shaped by the orbit. Well, some matter, perhaps not in the equator, but some slow, some matter that has relatively small velocity, that after, well, then has this shape, equatorial shape, because there is, of course, the binary system, this is the binary system, and this is the ejecta. Then this will be the shape of the first slow ejected mass, shaped, no, because it's rotating. And afterwards, there is a faster wind that finds this, and then there is this shock. Well, this story of the geometry is not so relevant, but it has sense because it came, the idea, after some observations that followed this geometry in radio. Okay, so this is the origin of this. But then now, more recently, well, basic in this first idea, so the idea came from these radio observations. Then they made a paper that is published in annual reviews of astronomy and astrophysics, where they analyze different aspects of novae. And well, this is complicated, but the idea is this, that you need this kind of internal shocks, is what was mentioned. You should have some, in some way, something special there to have strong shocks. So then they have, well, not so, there is also a reverse shock, like in supernovae. So the idea is this fast outflow, okay, that will find the slower outflow, so because if not, there is no shock. If you eject, no shock. But you should just eject one first part of matter and then another part that sweeps the lower one. So this is the model, but there are, except these radio observations, but I have more details about that afterwards. But this explains this is a way to interpret these observations in several novae, in the sense that you can have a relevant shock here that Metzger in his models, as we did, no? Well, others do in the case of red giant companion, you can do it also in novae that have not a red giant companion. Well, anyway, for RS Oph now, so this is just to finish to understand why classical novae can be also gamma ray sources in this MeV range, okay? So this is this part. And now let's move to the observations, only in one case, as I was mentioned, of this RS Oph. So in this case, there have been, probably there are more papers, but 3 papers about the observations. First with Fermi, of course, Fermi detected this nova, but this was not new because since, as I mentioned, since the launch of Fermi until 2021, so from 2014 to, there have been 7 detections of novae. But this is the first one that it has happened, no? The detection with MAGIC, so this Cherenkov telescope in the Canary Islands, okay, it's an international collaboration, and HESS, that is in Namibia, it's in Africa. It's another Cherenkov telescope. 5, okay, perfect, no, I have not many. So this, and then I wanted to explain, but it's what I mentioned at the beginning in the introduction, but fortunately I didn't put details because there wouldn't be time. That when he was here, when Santa Tichev, there was this previous eruption of this nova that now has been detected. We made this prediction, and with numbers, prediction means numbers, not only saying we are scientists, so some prediction I will show you now, that this nova, really, we were not doing the exact model. So it was this model of the fast and low. This is to explain, and this has not been completed to my knowledge yet. It's just an idea that explains that this could happen, but how do you are able to have these 2 ejections? This is not so clear. But what we did here was just from the observations, based only on the observations of this eruption in 2006, to see that there, the behavior of the temperature deduced from its rays, which came from observations with an X-ray satellite, and the temperature deduced from the infrared lines. So there was another approximation used there that is not valid when you have a particle acceleration. And then, well, the Rankine relations, well, there are some aspects there. And then one could see from there, from these observations, that there should be particle acceleration. Okay, there should be some shocks. And this is what we're publishing these astrophysical journal letters. Well, and this is interesting for other aspects because it's a kind of like micro quasars with respect to quasars. It's a miniature supernova remnant, all happens faster. Well, there are many interesting conclusions. So the important thing is that this, in fact, this we didn't publish it in a proper paper. This was done afterwards. But anyway, it was already mentioned in the paper. He made this prediction for Fermi lab that was not existent yet. And then now, this is what when Sam I talked about, because he was aware when we presented that in a conference of Heidelberg meeting that was made in Barcelona, organized by José María Paredes, International Meeting of High Energy Astrophysics. And this is the prediction, okay? And this is the observations. The prediction was just the low part, say, of the gamma rays. But also here, now, it works. So what this should be done, and has been done by the observer, just feeds on. But what I mean is that we already predicted that, and this has been observed, and so it's considered this special. I'm very happy to have given him the idea because he didn't know anything, so to speak, of novae. We were trying to find a topic about novae in the stage, and there was this eruption. Let's look at the observations. And then it was this more interesting than any other topic we could have worked. No? Okay, so this is then, well, yes. So the conclusions are here, just that no gamma rays can provide really information about novae. So that there are observations, but only these observations by now of high energy gamma rays, so those related to particle acceleration. No, now I put this and not to forget, because some of you, the ones that know me, will be, of course, know that I was working that, but these last years, it has been really busy, and I couldn't end without mentioning XTP, which is together with colleagues here, Pepe, Daniel, bueno, Alex, and here, and Alessandro, in the future, present future, hopefully. It's not yet approved by China, but we are already in phase B2, which means that it should have been approved already and have funding, which is not the case right now, the funding that we will need. But anyway, we are working in this mission, and I'm the PI of the instrument, which is something that gives a lot of responsibility. And also now there is a possibility that they have copied in between quotes what we had already collaborated before in proposals of NASA, and now there is a real proposal for a probe mission that will be, the result will be known, well, for phase A, it will be known in this summer, probably. In fact, we have already worked in phase A, approved by ISA of LOFT, which was a X-ray mission that has been the inspiration for two of the instruments of this Chinese European XCP. Okay, so, and you mentioned I will be happy that all the missions you mentioned were real. They were proposals, a lot of different proposals for gamma rays, and we have learned a lot, but by now, no one has been approved yet. Okay. Thank you.
Thank you. So we have time for a couple of questions.
Well, thanks for the talk. So my question is related to the rates that you talked about at the beginning. So I think really you said that classical novae, you have like 35 per year, and recurrent novae you have observed like about 10. Right. So is this difference in rate due to some observational bias, some like they're like some physical?
A very good question. In fact, this one, no? Yes, this, we don't observe, even that, of course, now there are a lot of observatories, automatic observatories, novae, but the problem with novae is that several of them happen in the center of the galaxy, the zones of the galaxy that we cannot reach because there is extinction by dust. And then several of the novae that we are sure exist are not detected. So this is so it's an extrapolation from other galaxies, observations of probably in other galaxies that are similar to one. And then this I have been in these years, I have seen, change this number from 20 to 40 or so. Even I can check it's Alan Schafter, because you know, he has made different papers, and the last one I think was this plus minus 5 or something like that. So based on extrapolations from other galaxies.
Then what explains that, like the difference between both?
But no, this, in fact, this is just it's misleading. I see now. This perhaps I will present it another way in the future, because this is not some measurement. This is only based on humans' capability to observe. So we could change now to 150, for instance, if we were in the year 2050. If you consider that since 1900, no, you can observe. You have some means of observe. I mean, even if it's well for supernovae, of course, the Chinese, no, in the year 1000, they detected the crab. Well, but for novae, this is not the case. It's not so spectacular, but there are no records. Okay. So it's just going back to the epoch where there can be records. So this is just, I remember, it's not based on the how many happen based on physics. It's just a definition that if the recurrence period is smaller than the time when you can do observations, then it means that you can observe it. So yes, it can be misleading. You don't know.
In the case of type 1 supernovae, we examined the anti-coincidence shield to see if it was possible that some supernova was hidden by the dust. Is there any possibility, or do you have any plan to examine the?
This is very interesting, but the problem is that the distance At least with integral, with COSI it will be a bit better. I don't have now the numbers, they have papers, not very predictions. But since the distance of detection are shorter than 8 kiloparsecs, for instance, then, and also this 511 kV line has a very short duration. I didn't tell you the details of that. I just mentioned this beryllium that is 2 months because it's lifetime, but the positrons come from radioactive nuclei that have much shorter lifetimes, as 1 hour and a half. So the emission is quite bright as compared to that of beryllium, but lasts for just some short time. 2 days or so, but the light curve, you see it really decreases very fast. So you should really have a powerful gamma ray instrument to detect up to these distances. This perhaps COSI can perhaps do that because it has a wide field of view. And then you can observe if it's, for instance, you have a detector monitor, no, the galactic center in gamma rays, and you can detect up to this distance. Then it could be we had said that in the old times when we expected that this could happen, no? That it would be a good way to just determine the rate of novae also in our galaxy, because we will see many more. If it's true what you say, yes, no, because these nuclei are there, absolutely the ones that produce this animation that gives a line. Or if not, like through the Lithium line also. Yes.
Yeah, so I have a question about the recurring nova as well. So you mentioned that there is one expected to occur this year, but they're not really periodic. No, they are. If you look at RS Oph, it was 15 years between the last 2 events and 21 years between the 2 before. So how do you know that one is going off this year? What is are there some telltale signs, or what is the mechanism?
In fact, now there is, you mentioned that with you, another, one of these historical, of the 10 you mentioned, the Corona Borealis, or that had first previous observation was in the 40s, I don't remember, 48, for instance. Well, of course there were telescopes or whatnot. And now, so I mean, there is a lot of, there is perhaps something in 900 or something. So it's very imprecise. But what they do, the observers that follow these stars, because they are bright, this one is closer than 1 parsec, so they are seen now, differently of normal novae that you don't see them before. No? But these ones, these symbiotic, in fact, these binary systems are known, some of them, and can be observed. And then they see some flaring, some pre-flaring, something, the light core, but there is controversy now, and we are expecting the last year of interest, because starting, for instance, 1 year or 2. And there is some guy in Louisiana State University that is so far in this law saying, no, I have seen a flare, and then it should be next year, so they don't know.
Okay.
We don't know.
Okay. But there is some activity, you see something.
Yes, you can see if it's one that is visible already, because you know them. So you can go there and then you observe them. Having the means to know it. You can see changes in the light core, in the visual light core, or not well. Yes, it's not so clear.
Yeah.
Any more questions? No, let's thank again Margarita. And we have to be there. We hope.
Stop share. Well,
Ay, el
sí, bueno, espera, stop share.